There's a lot behind evolutionary computing. I'm very excited to have Professor Schrum here with me. And Professor Schrum, maybe we can start off just talking about what got you into evolutionary computing.
Let me see. Good. All right. Awesome. Yeah, I mean, I love to think and talk about evolution because the way to motivate it as a research area is that if you look around you, evolution is really the only system we know of that is capable in an open-ended fashion of generating complex intelligence. We don't, fully understand all the details, right? But, we know that we got here somehow, and we're trying to figure out how we can have intelligence emerge out of a long history of descent with modification. And so we're trying to, in some ways, just be inspired by evolution, inspired by reality, inspired by nature, and go, wow, if we could only harness the power of this in our problem-solving systems, we could really make great breakthroughs. And we have made great breakthroughs. It's just that we also learned some surprising things about, I guess, reality in addition to that. Because it turns out that evolution is useful in many domains for optimization. It solves lots of problems. There's a long history of it, as Amir mentioned. And I did look up some applications in radio technology specifically where it's done interesting things. But evolution is also good at discovering the unexpected. And that's really where it's sort of fascinating as a problem-solving approach, because you're not necessarily always focused on a clear, singular goal. You're exploring lots of possibilities, and sometimes you have to, but humans are often goal-focused. We have a very specific application in mind, and so sometimes you have to think of interesting tricks to make this sort of naturalistic process bend towards your will in a way that solves the problems you want to solve, as opposed to just uncovering interesting things for their own sake. And in terms of history, I mean, I've applied, you mentioned how not everything is transformers, not everything's neural networks or machine learning. One of the things that Risto Mikulainen is an expert on is neural networks and neuroevolution, combining evolution with neural networks. And so in general, a cool thing about evolution is that it can be kind of combined with almost anything. It just takes a lot of cleverness to figure out the way to get the most bang for your buck out of it.
And so let's slowly start to bring the discussion back to, what we can do within this radio and mesh space and in this manufacturing space with evolutionary computing and genetic algorithms. So far you might be listening to this and you might say, okay, well, this sounds like another kind of AI. It's it's the kind of AI that searches for a lot of possible solutions and then finds some good ones and compares them to each other, and then generationally keeps making small changes until it gets to something good. And that's roughly the case. But how does that apply to the design of an antenna? Or how does that apply to the design of even a protocol? Meaning we're building hypermesh, there's meshtastic, and so on. How does that apply to protocols? How does that apply even to the physical device of the physical design of those devices on that table? And the answer is, it applies to all of these things. Because as Professor Schrum just described, in antenna design, what are you trying to do? You're trying to get some ratios right. You're trying to get a coil or not a coil, a material or another material, a length, a certain degree of curvature or a certain degree of taper. And these are all elements that are geometrically specifiable. Now, what you could think is that, okay, let me start with an antenna that looks like that, and it's defined by a set of numbers, and let me start perturbing those numbers and generate 6 more. And of those, is there any one which is better? And if there is one which is better, you might take one and the second best and combine some elements of them as if through a crossover. A mother and a father have a child, and that child has some qualities of the mother and some of the father. Sometimes they end up being better and sometimes they end up being worse. And so you go through this multi-generational evolution in this way, which leads to betterment. So that's kind of the antenna design example. But perhaps you could tell us a little bit, for example, today at Spec5, we design our cases with CAD. Theo, sometimes when he feels like it, will take up a CAD application and will design a case. Daniel designs cases. So if you look at what that process looks like today for a human engineer, measuring everything and so on and so forth, are you aware of any processes, or have you done work that would design physical constrained devices and just produce a whole bunch that one can pick from?
So I know there are applications in things like circuit board design where you're trying to fit a functioning design in a minimal area. And there's also problems in sort of job shop layout where you're, once again, trying to figure out where to put these things in a physical space to maximize utilization. And that's kind of similar to like designing a device to fit a certain form factor. And as you said, as long as you can specify these things, you can assign a number to them, you can generally figure out a way to evolve something to solve the problem. You have to have, so the fundamentals of what you need for evolutionary computation to work are a fitness function, which is essentially a utility function. It's a way of measuring how good something is. And then you need a representation, which I mentioned before. It could be a list of numbers. It could be a more complex thing, like you could have a graph type representation or a tree. You can even evolve code. That's what genetic programming is, evolving bits of code. Now, often you can evolve code as a tree structure. That's kind of a little trick there. But you can have different types of representations that you evolve. And there's also ways to do evolution in combination with LLMs, because they obviously generate code as well, and you can have you could evolve the input prompts to an LLM and get it to give you output. Now, as far as going back to the form factor issue, so you have your representation, you have your fitness function, you need variation operators. And so it depends on what you're trying to optimize. Do you want to like make it fit in the space? Do you want to minimize power usage? Probably all these things. And if you have more than one objective, then there's a whole branch of evolutionary computation for that called multi-objective evolutionary optimization, which we can talk about more. It has some benefits over other forms of multi-objective approaches. But yeah, it basically comes down to, can you specify it numerically? Can you measure it? And sometimes there's also a question of how long does it take to evaluate a solution? That could be a bit of a sticking point. Can you use a simulator to ask the question, how good is this? Or do you actually have to go out in the world, hold it in your hand, fabricate a prototype? That can be a bit of a limitation, because you have to generate lots of failed solutions to find the good solutions.
That's a very good point. So in the example of a case, yes, a genetic algorithm could design many, many cases, but some of them would look pretty strange, and unless you have some sort of a software-based quality check or constraint, it would really have to be to a human to look at those designs and say, I didn't like that one and I liked that one. But once humans do that enough, that feedback can also kind of be learned, and it can become a filter in future?
Yeah, there's work in these things called surrogate models, where if you have some sort of really expensive evaluation function, then maybe what you can do is try to train a neural network or some other model that tries to encapsulate the human rating system or the rating system of whatever your expensive fitness function is, so that it can predict what the fitness function might be. And of course, there's like trade-off issues between the quality of the real evaluations and then the fidelity of the surrogate evaluations. But it's sort of an iterative back and forth process where if things diverge too much from quality, then you have to up the number of training examples you do. But if you ultimately you hit a threshold where if you have enough data, hopefully you can automate that process, and then that can lead to new designs. Yeah.
So maybe I'll ask you one last question, and then we'll turn it over to the audience. We talked about what evolutionary algorithms are. We talked about the fact that they've shown great success. They're separate and apart from transformers and deep learning. And for over many years, they've shown success in electrical engineering, in materials design, in aviation, in even the design of antennas. And then we took two examples of, okay, in our case, could we design, an enclosure with GA, and could we, put some constraints and learn around those. The other thing in our field is, a protocol. So something like MESHTastic or MESHCore, or the protocol that we ourselves are designing. Now, generally, if you look at how protocols are specified academically, you've got the protocol diagram, you've got, exchanges of messages happening and so on. If you took something like that and you created a spec of a protocol and you defined some characteristics of the channel, because in our case, the channel is wireless, and the number of nodes as a variable, because as the number of nodes increase, the per node capacity in the channel decreases, the percentage of collisions will go up. There are some physics that would happen in that way. Is that the kind of thing that you have any knowledge of GAs or evolutionary computing having been applied to evolve an entire efficient protocol?
So what I'll first say that's at the edges of what you mentioned selecting, having the right channel frequency and having, having various nodes in a network, and so basically you're doing routing. Those applications, which are at the fringe of what your question was, have definitely been done with evolution specifically. So evolution has already been applied to problems in routing, and for both for wireless networks and for channel and spectrum selection, things like that. So they can be part of the process on that. But as far as a protocol is a set of rules, and you mentioned how you often have these diagrams where the structure of the protocol is like sort of a graph, and those are representations that can be evolved. And the question is, how do you encode a rule, and how much variation do you have? And so there's a mixture of human engineering and intelligence from the AI. And what's interesting is that in a lot of research. For like people who are doing research in genetic algorithms and evolutionary computation, they often care about, how much can I make the AI do? Like, how much can I accomplish without injecting too much expert knowledge to drive it, cheating, essentially. Yeah. But of course, people who want to solve real problems in the real world, we don't care about that. We want to cheat as much as we can. We want to inject that human knowledge, but also leverage the AI techniques to solve the problems. And we can definitely, think about, okay, what are the possible forms of a rule? Is it like, a set of 10, 20, like sort of primitives that you could have? And as long as you can sort of break it down into, here are like my primitive rule types, and then here are the parameterizations of those, and you can have so there's the ordering of it, there's the selection of the rule primitives, and then there's the parameterization of the rules. All of that can be handled by the AI via a search process. You just have to make sure that you give it a sufficient set of primitives, and then maybe you inject some more expert knowledge, and your primitives, quote unquote, become fairly complex primitives. And there's even precedent for this as well, because one branch of evolutionary computation is genetic programming, which involves literally evolving programs, often with a tree representation. But even back in, I want to say the 80s, there was work in automatically defined functions where you have your very simple function primitives, but they can have ways of combining with each other into reusable subroutines. They can be combined into rules, and of course, extra complicated human rules can be injected as well. So you just have to have some sort of language of rules to select from, or they're basically functions. So yeah, it fits right into the genetic programming framework. You have functions, rules, you have parameters, those get randomized, the order gets randomized, and the structure gets evolved. And in theory, you can discover a lot with that.
Fantastic. So I thought maybe I'd ask the audience a question. Just given this discussion, is there anything you think of that you want to design that you think is hard to design, that you want to ask Professor Schrum if it can be done with genetic algorithms?
Have a portfolio company that's working on drug development for oncology, and they're trying to, of course, they can generate, some molecules that they think might work for some conditions, but it ends up being a super high number, and that still needs to be kind of brought down to a testable limit so you can make some progress generating those physical molecules and then taking them to the testing side of things. So I'm wondering about your thoughts on, taking maybe, 10 million generated ideas down to something that might be actionable.
It really depends on the fidelity of your fitness function, or what you can measure and how much it costs to measure it. I actually have a colleague who's doing some work trying to evolve molecules that have certain optical materials properties, hyperpolarizability and things like that. And what they're finding out is just that some of these some of the software out there that can take a chemical structure and compute some value for you, there's limitations on how accurate that is, limitations on, and those issues with how long it can take to do. And so, but if you're gonna fabricate and test some of these anyway, maybe it doesn't have to be that accurate. Maybe if you just make a fitness function that's good enough at ruling out the bad candidates, that would help. And so that could be a filtering process. Now, it sounds like you already have the molecules, and so I'm talking about this other application where we're actually evolving the molecules, trying to find the properties. If you already have a lot of candidates to consider, and you're simply trying to, I guess, optimize which ones you pick, there's a question of, there has to be a population. And so if you could think of a way to formulate your problem where here's a population, they are evaluated, and they generate new candidates, then you can use evolution. And so that would take some brainstorming to figure out how it fits into this idea.
In the past, I guess there's been some use of, machine learning or AI in order to design, there's wind blades for wind power. There's, tandem use of solar panels. There's geothermal. There's water turbines. I mean, all of the above. I guess you could come up with a more efficient design, but in some of these areas, for instance, near major metropolitan areas, some of the concerns aren't is it efficient? It's well, this doesn't look nice. If you change the parameter to say well, is it aesthetically pleasing? I don't know, is there I guess interest in that area for, designing things that could solve problems do we have enough energy in our major cities or near our data centers or whatever?
So I can say that at the Genetic and Evolutionary Computation Conference, which happens every year, they have for many years in a row had this competition on, I think it's wind farm optimization. And I don't know the details of exactly what that entails, but they're definitely interested in applications in the energy domain. More to your specific question, well, because there's kind of multiple issues here, right? There's designing the components. That's very straightforward to do. It's basically an optimization problem, and evolutionary computation can be used as an optimizer. And so, yeah, if you want to optimize the shape of a wind blade and you have a simulator, you can, run that optimization independently of anything else. It sounds like the more interesting problem there is a question of how do you lay out your power infrastructure, and also you mentioned issues with aesthetics versus power generation, possibly with other objectives. And so whenever you're solving a problem with evolution, it's good to have things you can measure numerically, but sometimes you have to ask yourself, is this an objective that I want to either minimize or maximize? Is it a constraint where I absolutely have to have values in a certain range? Or is it some other measure or metric where a lot of different options are possible, and for some reason, maybe I'm actually curious to see what the possible variety is. And so if that last thing's what you care about, there's this whole field within evolution called quality diversity optimization, where instead of aiming towards one goal, you are sort of finding a way to categorize the range of possibilities. So for example, like density could be a property that you measure, like the density of the placement of different things, or you could be measuring the trade-off between wind and solar or in some other options. And so those are things that you can measure numerically. But let's say that your actual fitness is maximize power production. If you throw one of these QD methods at that, it doesn't give you one solution. It gives you a whole range of solutions that fit in, that across that spectrum of, like, here's more dense, less dense, here's, you know, more on the wind side, more on the solar side. And then assuming that you had a way of measuring aesthetics, you could incorporate that too. I mean, density might be part of it, because if things are really clumped close together, maybe that's a bit ugly. And so, you know, having a certain, you know, dispersing the different sources of the energy might be something you want to play around with, a dial that you want to choose from. And so you get your results, and then in the end, you have a human decision maker come in, look at this archive of collected possibilities, and you go, oh, now that I know that this is like the best I can do with this level of like density or this percentage focus on wind versus solar, like I would prefer this solution. So you're sort of like exploring possibilities. And a similar thing can happen with multi-objective approaches, where if you legitimately do have multiple objectives, but they might be in competition with each other, there's both a field of evolutionary multi-objective optimization where you can explore trade-offs between those objectives, and there are ways in which that field is combined with the quality diversity optimization field, where now you're looking at all sorts of possibilities, not only objective trade-offs, but also, you know, different ranges of whatever your diversity measure is. So I think it's just a matter of how big you can imagine, like, breaking the problem into components and then figuring out how to, you know, isolate the solutions you care about.
Fantastic.
Thank you.
Yes, please.
Have you seen, or you've seen where somebody has taken, tried to take, say, a pre-populated form similar to an incident command form or a disaster or whatever, take that pre-created form, the data goes into it, it's sent through a mesh, and it comes back out where, whether it could be something similar to a facsimile, I don't know if that even exists, or in slow scan TV as we use in high frequency radio. Have you seen anywhere where we can put that, you know, application? Because in emergency management, we're thirsty for this. We need that redundant path. And so if we are not able to fax, or we're not able to access a satellite or phone service, do we have the ability anywhere to take a prepackaged document, fill in the data, and send that document?
Yeah, so I think what you're talking about is at the edge have some sort of a prepackaged form, and then based on environmental and other sensor readings, location readings, fill out the form, or would there be human involvement also in filling out?
There would be human involvement. Let's say they just wanted to say they need 3 pallets of water at Suki School.
Sure.
And we wanted to send that packet of information, but it goes on a specific FEMA incident command form for a request.
Yes.
So if I was able to pull up out of this pool that form, put the data I needed in there and sent it, they would know, or we'd be able to, I'm going back to my old DOS days, but able to match it up by line to try to have that where you could exchange it, someone could read it.
Yes, I think that definitely that can be done. It would not require an evolutionary approach, because you wouldn't really be choosing from thousands of possibilities and trying to evolve and make them better. But what you're saying, yes, definitely can be done. If there's a last question, we'll take it. Otherwise, for time, we'll... Yeah, please, go ahead.
I'm looking at this node map right here, and I'm wondering if evolution could possibly be used, and I don't know, maybe this could be at the application layer that is future designed, but could there be a evolutionary factor in there to maximize and make more efficient the way that the nodes communicate? For instance, you know, from all the way up to all the way down, changing the frequencies, changing the, you know, the long fast to something else.
For sure.
But also to immediately adapt. Let's say we have flooding or some sort of emergency, to immediately route some of those emergency messages to where they need to go. And incorporate that, like I said, maybe at the application layer, if that gets a future design.
Yeah, you'll recall that when Professor Akela was giving his talk, we talked about this little agent that could sit and modify all the parameters and make sure that you are optimizing something. For example, you could optimize bandwidth, you could optimize range, the number of nodes you connect to, etc. There are very many techniques that can be used for that, one of which is based off of embeddings and transformers, but I'll let you address the GA side of it.
Yeah, essentially you could have, I mean, it sounds like that's part of your protocol. And so Amir was already talking about ways you could evolve a protocol. It'd be, so that could be incorporated. Essentially, it sounds like a control policy. Like you want to have some way of modifying the behavior in response to situations you're experiencing in the moment. And that makes me think of reinforcement learning, which is its own field, which you can, you know, there's a lot of reinforcement techniques, reinforcement learning techniques that exist independent of evolution, but there's also ways of combining them. There's evolutionary reinforcement learning, and there's also using like neuroevolution algorithms to create agents that would monitor things like this. And so if you want it to be, I guess, dynamic and adaptive, what you would need to do is train the agent with some sort of maybe historical data, maybe also synthetic data of like just how bad things can go, things that can go wrong, to make sure it's able to respond to those situations. But I suspect that explainability would also be very important in an application like that. And so I mentioned that you could evolve programs. Genetic programming would be another way to create a policy. And then you could actually look at the code and critique it.
I just want to add one comment, and this also is a plug to some of the uses we have found for genetic algorithms in our own systems, computer systems work. We've been using it to generate what we call instance optimal policies or algorithms. You know, anytime you run a system, it's facing an environment, and the environment changes, and you want to understand what new protocol to use in that environment, and generate that protocol and deploy it. So we've used it for things like caching. You know, caching is also caching, the definition of an environment for caching is the sizes of the objects and whether it's video or text and so on. And just each time I experience a new environment, instead of figuring out what algorithm to use, I just ask a genetic algorithm-based agent that generates code that represents the algorithm that is ideally suited for that. Where I was going with that is essentially what you're saying. In a mesh kind of an environment, let's say I have a prototypical mesh network in the usual case that has certain number of links and I'm able to communicate, and I have a particular protocol I've deployed to run well on that. But suddenly I'm faced with a disaster where, like flooding or something else, where a huge fraction of that infrastructure goes away, and I'm left with a very different environment. And I want to understand, okay, what is the right protocol to use to get communication going over there? We've found use for genetic algorithm and kind of being able to search through the space of something that can custom fit that new environment.
That makes me think of another application of quality diversity algorithms, where there was work done where they were training a robot to just do basic locomotion, but they wanted it to walk in different ways. So it was like a hexapod robot, and they were saying, oh, here's a gate that uses 3 legs, here's one that uses 4 legs, and there's all these different gates. But they had this quality diversity algorithm that collected basically how far can you walk with all these different, qualitatively different gates. And then they showed that, oh, if you have a robot where some legs break, you can switch over to another thing in your archive. And so you could imagine a situation like this where you have nodes in your network and you're saying, I want to have the policy that optimally uses these nodes and ignores these others, or you could just characterize the node usage of different policies for the network, and then if you have this collection, this archive of policies to draw from, when something breaks, you already have a solution for it ready to go.
Well, fantastic. Thank you so much, Jake.